if we're given numbers in the real number system, they're still complex, but they're just real numbers, and we can order them. For instance, if I give you the numbers -3 and 10 and -42 and 17, you can put those in order from least to greatest, and you have some idea of how they fit in relation to each other. But for complex imaginary numbers, we don't have that same organization. We don't know if this number is bigger than this number or how they relate to each other unless we graph them. So we're going to learn how to graph the complex numbers and then look at the resultant, which is just the sum of the two numbers. Okay, so let's graph these first. 6 minus 2i represents a single complex number, complex imaginary number, and we're going to graph the real part of that number on the horizontal axis or the x-axis, and we're going to graph the imaginary part, including the sign that goes in front of it, on the vertical or the y-axis. Okay, so here's what that looks like. Our answer is going to be a vector that starts at the origin and then goes to that point. So if I start at the origin and I go 6 in the real direction and -2 in the imaginary direction, then I get this vector right here that represents this number. It's not just the point that it's headed to, but it's the vector from the origin to that point. So that gives us a length of the vector, it gives us a direction, and that's how you graph a complex number to understand it. Now let's change the color of our vector here, and let's draw -4 minus 3i. We're going to start at the origin. We're going to go -4 on the real axis and -3 on the imaginary axis, and that gives us this vector. Now, when I find the resultant, I'm adding those two together. We can add them together algebraically. You did that in the first section of this chapter. So if I take 6 minus 2i, that's a complex number, and I add to it -4 minus 3i, the first thing I want to do is get rid of the grouping symbols. Well, there's nothing except a +1 in front of this parentheses, so I can just get rid of it. Same thing here. If I multiply everything by a +1, I'm going to get -4 minus 3i. So basically, we can just drop the parentheses. Now I can collect my real parts and combine them. 6 minus 4 is 2. And I collect the imaginary parts, -2i and -3i, and that gives me a total of -5i. So this is the sum of those two complex imaginary numbers, and that's called the resultant. If I graph that resultant, then it too is going to be a vector that starts at the origin and has on the real axis a value of 2, and on the imaginary axis a value of -5. So the vector from the origin to that point to -5 represents the complex number 2 minus 5i. Now, if you've seen this in physics, there are a couple of ways that you can draw these. We're always going to graph them like this, not floating around in space. And when you do graph them, if you connect the arrows for each of the vectors like this, then you see you get a parallelogram. Now, a parallelogram, this is not a rectangle, but rectangles are parallelograms. So if you remember that, then it's easier to remember that this form of the complex number right here is called rectangular form. Last semester, when we combined these, we didn't graph them, but we combined these numbers, or we solved and we found numbers like this, and we called it standard form. So rectangular and standard form are the same thing, and that's graphing vectors.